But all right, I want to get into the lecture here. I've been kind of putting this lecture off because it's compile time computation, and compile time computation we'd have to talk about a compiled language. And Python is actually compiled, but the compilation step is not very meaningful. It compiles down to Python bytecode, which is then interpreted, and the mapping between Python bytecode and Python source code is very similar. So the compilation step isn't actually doing very much. That's in contrast to a language like Java and C++ and C. Those languages, C and C++, they're compiled down to machine code that just runs directly on the hardware. And Java is compiled down to Java bytecode, but the mapping between Java source code and Java bytecode is much more distant. And so that compilation step actually does a lot more. So to talk about really heavy compile time computation metaprogramming, we're going to have to switch into some more strongly compiled languages. So we're going to first pivot into Java briefly. And I know not everybody loves Java, and some people might not even know Java very well, just considering the prereqs that I listed. So if Java is not your thing, bear with me, and I'll try to go, we're not going to go too deep. And then we're going to pivot into C++. And again, I don't like doing it because I really like to focus on Python in this class, but it would be unfair of me to shortchange all the great compile time metaprogramming that you can do out there too. So let's see, let me hide these windows so I can see what I'm doing. Okay. So, I mean, what is a compiler? It's a metaprogram for sure, because if we think about what a compiler does, it takes in source code and then it modifies that code in some way and outputs more source code. So it's, or not source code, it outputs the target code. And that's like the definition of a metaprogram. Metaprograms treat programs like data. Here the data is the program that we're writing. The compiler is treating that program like data and translating it. So this is definitely metaprogramming. And it's nice because compilers often provide some interface for us to take advantage of the fact that they're metaprograms. We are often able to kind of interrupt this flow from program to compiler to representation. We can add extra information. We can talk directly to the compiler. And that allows us to do all sorts of crazy stuff. So to get started here, we need to talk about metadata, because this is metaprogramming. We've talked all about meta programs, but here metadata is going to start coming up. Does anybody want to offer what they think of as a definition of metadata?
Data about data.
Data about data. Yeah. I mean, if you stick meta before anything, you can probably bet that that thing is going to relate to itself in some way. And so yeah, metadata is data that relates to data. It's data about data. So like a classic example might be in a file system, you have files that contain data, like you've got, a text file with some notes or something. But the name of that file itself is metadata. I mean, the name is stored somewhere. It's data. The name is data, but it's describing the file. It isn't the file itself. So like file names, file sizes, file types, those are all metadata. So we're going to pivot into Java here, and I'm going to show you what the @ syntax does in Java, because it's a great way to get into Java metaprogramming. We use the @ syntax in Python to do decorators. It means something different in Java. So if you've written Java, you might have used @test or @override. Here we're using @my annotation. So I'm not quite sure where that comes from at this point, but we're just going to do it. And we're passing in some parameters here. And if this were Python, we would think this is a decorator. But it's Java. And so it's not so clear what this is doing right now. To figure out what it's doing, we're going to use reflection. And so it turns out, we learned reflection in Python, but reflection is also doable in a lot of compiled languages, Java included. So this code here, this is Java code that gets the class that we're in, and then gets the method that we're in, and prints out all the annotations of that method. So this is a reflection. This is a program, a Java program, inspecting its own structure at runtime. So at runtime, it's getting this a reference to the method that it is. We can do that in Python easy peasy. You know, the name of the function is accessible, and then we can call methods on it, access all of its attributes. In Java, it's a little bit more tricky, but we can still do it. So this self instance of method here is kind of it's a representation of the method we're in, and we're going to print out all the annotations. And like we would expect, this just prints out my annotation with these values. It turns out that's about all you can do with annotations in Java. So using this @ syntax here is not like a decorator. All it does is it marks whatever we annotated. So printing them out, inspecting them, that's really all these are useful for. It turns out my annotation is not a script that modifies this print annotations or anything like that. So that begs the question, well, what is this code? My annotation, where is it defined? In Python, it would just be a function that takes in a function. In Java, we define it like this. We say public @interface, and then the name of the annotation. And then you can define the things that we want to take in as arguments for that annotation. And that's it. There's no code. There's no script. It doesn't do anything. Annotations in Java are just metadata. They only describe things. So by using this @interface, my annotation, if we annotate something with my annotation, all we're doing is marking it. You know, we're just putting a little flag there, and then we can you know, add some fields to that flag. So, well, sure enough, I opened the door and bugs are flying in. Okay. So if annotations are only metadata, they don't do anything. They're not useful. You know, what's the point? You know, Python, it was cool because we got to manipulate the thing that we were decorating. Well, there's still cool stuff we can do here. We just need to add something else. We need a meta tool to use that metadata. So the analogy here is if our metadata is file names, then Finder, the Finder app, or the whatever it's called in Windows, however you access those files, that would be like the meta tool. And so you can change the name of files, you can copy, duplicate files. That's like meta operations on the data through the metadata. So we'll see an example here. That was kind of a vague example, but in Java, these things are called annotation processors because they process annotations. They do something with that metadata. And so it turns out they're just classes that extend abstract processor, and then they implement the process method, takes in some information about the environment that we're in and the annotations that we're processing. It can't change the code that was annotated because, again, it's just metadata. But the process method can do other things. It can have side effects. It can throw an error. It can generate code. So let's think of some examples. Like I said, if you've written Java, you might have used the @ syntax to write @test if you're doing JUnit testing. And I think everybody in 2110 has to do that. So you've probably written @test before. What is that doing? We now know that that @test is just metadata. We're just flagging that method with this is a test, you know, look at this as a test. But it's not actually calling the method, it's not changing the method, it's not doing anything. It turns out that JUnit is an annotation processor that knows to look for methods decorated with that test, and then it has the side effect of running that method and displaying the results. So, and this goes to show, like, if you just run a JUnit test file, it doesn't do anything. There's no main method. But if you run the annotation processor JUnit, it does do things. So the annotation processor is the meta tool, and it's using the metadata. This is similar to how we might see things done in Python, but in Python it will all just happen in Python in the interpreter that we're running in. In Java, there has to be a distinction. There's the Java runtime and there's annotation processors. So let's think of another example. We've got at test. What's the other thing that most people have written at for? Can anybody name another thing that you've written an at for in Java?
Override.
Yeah, at override. Um, if you don't remember from 2110, you can say at override before a method, and that will assert that the thing that you have annotated actually overrides some function from your superclass. And it'll throw an error if it doesn't actually find some method that it's overriding. But we know that at override, it doesn't do anything. So how does that happen? Well, it turns out that the compiler itself is an annotation processor. It has its own process methods. And one of those process methods is it looks for at override annotations, and it checks up the inheritance tree and makes sure that you actually did override something. The side effect here would be that it throws an error if you didn't. So just because annotations don't do anything by themselves doesn't mean that annotation processors can't have these really nice side effects that we actually want. Questions about JUnit and override checking? Or annotations in general so far? All right, cool. So I've got, I think, one more example of an annotation processor. It's called Cofoja. And it's a library written by some Google engineers. And it implements a couple of annotations: requires, ensures, and variant. These things are things that you can annotate methods and functions with, and they will somehow assert that all of the requirements are true, and that after the function is called, it'll ensure that the post conditions are true. Basically, this is implementing pre-checks and post-checks for method calls. And this is really nice if you're programming some environment where you want to make guarantees about the state you've left things in after certain code gets called. So how does this work? I mean, like we said, we couldn't change the function that gets annotated. It's just metadata, and the side effects are not very, the side effects that we can have are usually like throwing errors or running the code, checking the test output. Here, the side effect that Cofoja has is it generates Java bytecode and inserts it into the program. So it generates the checks that are required to ensure things, and it changes the code after compilation. So it doesn't modify the function itself, it inserts bytecode. And that's something it can do. That's a side effect. So one interesting thing here is that the requires annotation, it takes in as parameters things that it must require to be true. But how does that work? The conditions would also be Java code. Let's see an example. If we say at requires, we can pass in this this list of things that we want to require to be true. What are these things? I mean, it's kind of an obvious question. They're strings. I mean, that's it. It's just a string. But it's more than a string. It's actually representing Java code. And if we look at the method header, it makes references to variables that this function is taking in. But these are just strings. So how does the Cofoja library actually figure out like what we're talking about here? How does it go from this string to some bytecode that actually checks that the current buffer is not null? Well, Cofoja uses the compiler that it is annotating, that it's registered with. So the annotation processor, Cofoja, is generating and inserting this bytecode, but the way it generates it is it calls the compiler. So the compiler calls the annotation processor to figure out what the heck is going on here. And then the annotation processor calls the compiler to compile these strings into Java bytecode that then gets inserted back into the bytecode that the compiler is compiling in the first place. So I mean, the things can work together. The compiler can be used as a tool by the tools of the compiler, which is just nuts. Okay, so we've got this requires thing here, and it's going to insert some bytecode that asserts that these things are true. Let's look at the rest of the function here. switch token case comment. Does anybody want to take a guess where I got this function from? Where I got this code snippet from? We've got a switch statement based on some token. And if it's a comment, then we're doing some other stuff. Otherwise, we append the token to the buffer. Any guesses? Let's see, there's a chat. Let's see. Some compiler? Close. So I got this code snippet from the Cofoja library. This is Cofoja implementation. This is part of the code that is the annotation processor that processes Cofoja annotations. So that's actually even more meta than we thought. So first of all, the annotation processor is using the compiler to compile these strings. But also, the annotation processor is implemented using its own annotations that it processes. So this is an example of an annotation processor that annotates and processes itself, its own implementation. So that's definitely meta. So there's all sorts of levels of meta here. Compilers calling tools, tools calling compilers, tools calling themselves. And this will actually come back, I think it's next week. We're going to dive deep into compilers from a theoretical standpoint, and we'll look at compilers compiling themselves. But that's a later thing. I think this is it for annotation processors. Any questions about this? The question is, if you make a syntax error in this string here, in the requires string, would you get an error? How would that get reported? Yeah, it would get reported as a compile error. The problem is that that compile error might have a really long stack trace because it happened in the compile step of this code, which then called out to the annotation processor, which then called back to the compiler to compile these strings. So you might have a very long stack trace. I'm not 100% sure, but yeah, you would get some sort of compile error. And the report would be passed back through all the steps, all the method calls. Yeah, good question. Okay, so kind of related to annotation processors, a lot of what you can do with this stuff is code checking. So like Cofoja inserts runtime code that inserts checks. But if you look at like JUnit and at override, those did checks on the code before running it. They did pre-runtime checks of your code. That's a really common usage of this annotation processor stuff. And checking code like that is called static analysis, and it's actually a huge research topic. Like for example, you could have a code checker that looks for copy and paste bugs. Like maybe you have like the exact same code copied 4 different times, and in the first copy I is 1, and the second copy I is 2, and the third copy I is 3, and the fourth copy I is 3. That's probably a copy and paste bug. You probably meant to change I to 4 in that last one. So that's an example of something that you could check before even running your code. And this actually is done in huge code bases because little errors like that can build up, and there's no reason why you can't write a program to check for those things. So often that's done by extending the compiler in a similar way with the annotation processors. And this is a huge research area. It turns out finding bugs in programs is undecidable. It's impossible to write a program that looks for bugs perfectly in another program. And it comes down to the halting problem. If you're interested in why it's impossible to write a perfect code checker, definitely check out Theory of Computation. These analyzers will often do other things too. And so maybe some of you have heard of tools called linters. A linter is a code checker that checks the style of your code and the exact, not so much whether there is a bug, but did you write it in the standard way Is this likely to be readable to somebody else? That's a linter. And related to that, you have auto formatters, which not just check whether you wrote the code in a standard way, but change the code so that it's written in that standard way. So some examples of auto formatters are black, autoflake, isort. Isort, for example, if you run isort on a bunch of Python files, it'll sort all the imports. And that's nice because that way when other people read your code, they can always depend on being able to find imports because they're always going to be in alphabetical order. We're actually going to write an isort implementation in a later lecture. Not a full isort implementation, but we'll write a program in Python that will sort the imports of other Python files. So get hyped for that. We can also do type checking. So we've got tools like MyPy and Pyre. Python is not type checked. It's duck typed. You can pass anything in at any time, and as long as it has the requisite methods, it'll work. But sometimes we do want to actually make some guarantees about what types are actually being passed around. And so you can run Python type checkers that will check the types of all your method calls and method definitions before running your Python program. And it just gives you an extra level of confidence in the correctness of your Python code. And that matters because it's hard to write Python confidently. I mean, the types are weird. So these are all things that we can do with this kind of annotation, compiler hook style of metaprogramming. Any questions about this? Because we're about to move on to C++ metaprogramming. All right, cool. All right, C++. All right, I'll be the first to admit that I am not very good at C++. And last time I taught this lecture, I made so many awful mistakes. Like I had left out almost every single semicolon because I'm just used to writing Python. So feel free to call me out if I just say anything blatantly wrong. I did try to fix most of those errors, but there still might be some awful, just terrible C++ sins in here. So call me out if you will. Kind of the quintessential C++ metaprogramming is macros. And why are macros metaprogramming? Does anybody want to offer an explanation of why you might call macros metaprogramming? It's not so obvious to me because they're just part of your program. I mean, and they're kind of like variable definition. You define a variable, you define a macro. What's the difference? I would argue that, I mean, macros are metaprogramming because they happen before your program is compiled. So you're really writing two programs. You're writing your program, and then you're writing your macro program that defines what program you're actually trying to compile. That you're writing the process step that happens before your program is actually determined and written. And this can have a couple benefits. Computing things before you move to the compile step can speed up your program. That way you're not doing the computation at runtime, you're doing it before the program is written. And you can often save some typing. You can make your code very concise with macros. So let's look at some macros. All right, this is a C++ macro. We say pound define, and then some name. Usually they're in all caps, and then the thing that you want that macro to be. So here we've got maxint and some large number supposedly is the maximum integer. So now in main, if we see out maxint, what do you guys expect? This one should be pretty clear. We just expect that max int, and that's what we get. So that's what we expect. Okay, let's define this max macro function that will take in an n and compare it to the max int. And so this max will evaluate to true if n is the max int. Otherwise, it will be false. So this is a macro function. And in main, let's say we see out our call to the max function. Does anybody know what's going to happen here? We'd love to get a volunteer to take a guess.
Depends on like how the parentheses get interpreted, because you didn't put parentheses around the whole expression that the macro evaluates to.
Yeah. So what you're highlighting here is the fact that this macro evaluates to this value here, n equals maxint. That's what the value of the macro is. And if you don't know, C++ macros do text substitution. They just swap out the text. So here, this call to max on this number is going to end up just swapping that little bit of string with this string, n equals maxint, or it'll be that number equals maxint. And then maxint will also get substituted out. So the problem arises here because we've just inserted this equals into this C outline, and it turns out that equals takes higher precedence than pipeline operators. So this doesn't compile. Let's see, I'm blocking my own screen. Yeah, this does not compile because we did text substitution and we inserted an equals that then broke the flow of this C out stream operator. But just looking at that code, it's not so clear that that should have happened. I mean, we just called this function. This code looks like it should compile. So this is kind of the first example of when C++ macros can be really confusing. The way we probably should have written this macro was to wrap n equals maxint in parentheses, because then it would have overridden the operator precedence. Questions about this? All right, let's get to some more crazy examples. We're going to define this macro, square of x is x times x. Makes sense, reasonable. And in main here, we're going to print out the square of 1 plus 1. So what do we obviously expect the square of 1 plus 1 to be? I mean, 4. We definitely expect it to be 4. Does everybody know what's going to be printed? Here, instead of somebody speaking up, let's get it in the chat. Everybody chat what you think will be printed out here by this beautiful main function we've got. All right, yeah, I'm seeing some 3. Yeah, it is 3, but that's not what we would want really, because we're squaring 1 plus 1, and 1 plus 1 is 2, and 2 squared is 4. And we did kind of put this 1 plus 1 in parentheses here. This definitely looks like the 1 plus 1 should happen first. But the problem comes from the fact that macros do text substitution. So it prints 3, and that's because this text substitution ends up looking like 1 plus 1 times 1 plus 1. So the text substitution didn't really do what we wanted here. So this is another instance where macros get confusing. And like before, the solution would have been to wrap all of these x's in parentheses and then wrap the entire expression in a parenthesis. So that's how we would have solved this problem. Let's take a look. Let's write another square macro where we do that. And now in main, we're going to set x to 1, and we're going to see out the square of plus x. Now let's see in the chat, what do you guys think this will be? We got a not 4, we got a 6, got another 6. How many people are in this live, in this Zoom? A lot. Anybody want to argue for anything other than 6? To me, I mean, I think it could be 4, or it could be 6. 9. It's kind of tricky to see. It turns out this is actually undefined behavior because it's not defined what is supposed to happen if you use plus plus x multiple times on the same line. Because C and C++ make no guarantees about the exact order that it will execute the components of an expression. It doesn't necessarily go left to right. It could try to do them in parallel. This could be a race condition if there's parallelism going on here. So this is actually undefined behavior. You're not supposed to do it. And it's because this gets expanded into plus plus x times plus plus x. Again, this could be 2 times 3, or it could be 2 times 2, or it could be, it just depends on the order that things get done here. If these things get executed in parallel, it's totally believable that it could be 2 times 2, which is 4. So another instance where just adding parentheses to the macro doesn't always make it so easy to see what's going on. All right, let's move on. We've got a new macro here called ReLU. ReLU is a function that comes up in machine learning. And basically, it looks like a flat line for all negative x's, and then it goes up linearly for positive x's. Basically, it takes in any real number, and it converts negative numbers to 0 and leaves positive numbers alone. So it's basically bringing everything up to be at least 0. So defined a ReLU macro here. And we've got x is equal to -1. If true, let's say we're in some code base where we're in some if statement, and if true, maybe this is some real condition, but for here it's just going to be if true. We call ReLU x to bring x up to 0. And here x is -1. So we expect when we print out x, we expect to get 0. And we do. We get 0. So this if true evaluated as true. ReLU, if x is less than 0, that's true. So then we set x to 0, semicolon. So that worked. Now let's see this example where x is actually greater than 0. So here we should expect x to stay the same. X should still be 1. If true, ReLU x, else some unreachable code because we said if true, print x. I would ask what you guys think will be printed out here, but I suspect I might have kind of given it away in my tone and the unreachable print statement. ReLU will work how we expect. It will not change x. X will still be 1. But it turns out that this will print unreachable first. So this code that should be unreachable is in this else statement of an if true. I mean, the else of an if true should never execute. True is always true. This should always execute, and this should never execute. But it turns out that if you're not aware, in C++, if you don't use curly brackets around your if and else statements, then else's will associate with whatever if came immediately preceding. So here, it looks like this else statement is going with the if true. But actually, it turns out because this does text substitution first, the else will actually get associated with the if statement introduced by the macro. And so even though it looks like this print statement should never print, it actually does if ReLU, that if statement evaluates to false, then this else will become true. So that's why we didn't get reachable up here, but we did get unreachable down here. Oh, yep, semicolons. Yeah, all right, people are calling me out on, I told you. Well, and the other thing here is I'm printfing x, and x is an int. I don't think you can do that. I don't think you can printf an int. It has to be a char star. So yeah, I got caught out for this last time. I thought I fixed all of them. I guess I didn't. So okay, questions about this? I think this is the last macro. The takeaway here. Oh, the takeaway. Oh wait, there's one more. Oh yeah, this one isn't as interesting. We're gonna define this this max macro, and then we're gonna pound include algorithm. It turns out this doesn't compile because algorithm implements a max function, but then before we included algorithm, we defined a max macro and those things collide. Turns out namespacing for macros is actually pretty weird. This won't error, for example, if you switch the order of those two. If you include algorithm first and then pound define max, it's fine. But if you pound define max first, name collision. So this is the last example of confusing macros. So the takeaway here is macros are kind of not great. They're hard to debug, they're ugly. We can do better, basically. So there's one other major form of metaprogramming in C++, and that is templates. Oh yeah, and there's const and const expr. I think I'm going to skip this. Basically, const expr, if you define something as const or const expr, it'll be computed at compile time instead of runtime, which you could argue is metaprogramming because you're speaking directly to the compiler and telling it to do some computation. Other than just passing it a program, you're treating that program as data, yes, but you're also telling the compiler to do things. So that's a form of metaprogramming, const and const expr. And it's relatively new, very cool stuff. You can have code that only compiles certain branches if certain things are true. Like maybe you could have a const expr check the date, and if the date is beyond some date of deprecation of some other library, then it just won't compile some code. All sorts of cool stuff you can do here. But I want to move on. Templates. This is kind of a more traditional way of doing metaprogramming in C++. It's also pretty ugly. But C++, you just got to do with what you got to do. So this is a way also to compute things at compile time. And but let's just remind ourselves what templates even look like here. So this is kind of your stereotypical templated function. It takes in a template type name, and then it swaps these two references to these two type name T things. Basically what this is doing is the template will actually generate multiple versions of this function, once for every type that it's called with. So if we call beginning caret int end caret swap, then the compiler will generate a copy of this function with T replaced by int. So you can actually see it's kind of doing text substitution, but in a more structured way, than macros. But because it's doing this kind of compile time step, we can actually take advantage of templates to do compile time computation for us. So let's take a look. Let's say we wanted to, at compile time, add two numbers together. Here's your traditional add function. It just takes in two things. This will do it at runtime. So if we write this function, it'll get compiled into code, machine code, that adds these two numbers together. But if we write it this way, it's something slightly different is going to happen. We're going to write a template. And usually when you see templates in C++, you're used to seeing them with type name parameters, because that's what the feature was designed for. It's designed to make functions and classes that could be used for different types. But here we're going to actually take in some values, some ints, as the parameters to this template. And the thing that we're going to be templating is a struct. Why a struct? Because structs are defined at compile time. So the compiler will figure out what this struct value is at compile time. And that's just due to the fact of how C compiles structs and enums. You can't create new structs and enums on the fly in C++. They have to be predefined. And so this will all be computed at compile time. The weird thing here is that this enum, the value of result, is computed as the addition between these two templated parameters. So if this is computed at compile time, that means the compiler has to actually do this computation at compile time. And just for reference, this is how it's used. You can see out the adder struct, pass in 3 and 4, reference the result field. This will always be equal to 7. And that computation will actually have been done at compile time, not at runtime. So if you then go on to later reference adder, 5 and 6, reference the result, it'll be 11. But what will have actually happened is the compiler will have created a new struct with a new enum, with a new result at compile time for every instance that you call adder 3.4. So it'll memorize every addition that you need. The caveat here is that the things that you put in this template have to be const, because obviously the compiler can't compute these things at compile time if it doesn't have the data that you need at runtime. Like if this were x and x was computed at runtime, then the compiler wouldn't know what it is. So it would have to generate infinitely many of these structs, and it's not about to do that. Questions about this? This is definitely weird. All right, well, let's just dive into the last example. It turns out that this style of compile time computation is Turing complete. You can write any function with templates and structs and enums in C++, and you can force the compiler to compute things that are actually pretty complicated. So the other example I have here is factorial. So here's our kind of classic factorial runtime function. This will generate machine code that at runtime will compute a factorial. But let's say we need just some factorial value as a constant, global variable in our code, but we don't want to actually compute it at runtime. It would be too expensive. Well, we can create a template that takes in an n, and this template is for a struct factorial with an enum with a value, where that value is equal to, and then we call the template again on n-1. And it might be kind of hard to see, but n here must be const. And so because n is const, subtracting 1 from it is also const. And so this is all const. So this is all okay. Nothing actually requires the runtime here. So the compiler will actually gladly generate this code. Does anybody see a problem with this? It's the classic problem that always comes up with recursion. Where's the base case? Here we're just taking n, we're subtracting 1, and we're calling this template. The compiler would never stop generating code here. It would always just, okay, oh, now we need to generate a new struct factorial with n-1. Oh, now we need to generate a new struct factorial with n-2. And we just keep doing that forever. We need a base case. It turns out that in C++ you can write special forms of a specific templated thing. So here this says we can pass in an n to this templated factorial struct, or if you pass in 0, override that previous definition and do this other thing instead. So this is our base case. And then if you call this code, you could do cout factorial 10 : value. That will print out the factorial of 10, but it won't have computed it at runtime. At runtime, this will basically look like a constant that you hard-coded in, but you didn't hard-code it. The compiler computed it. So that's the ultimate benefit of all of this, is that we can have the speed of hard-coded constants, but without the ugliness of hard-coding. We don't have to actually check whether this value is the factorial of 10. I mean, if we had hard-coded it in, and then we wanted to switch to the factorial of 11, then we would have had to go back to our calculator, punch in factorial of 11, switch out the constant. Maybe we missed a number. What if it's a copy and paste bug? Here, we're actually getting the compiler to do all that work for us. We can trust that that really is the factorial of 10. There's no copy and paste bug, but we get all the speed of a hard-coded in constant. So something that's kind of cool with C++ programming. Again, I hate to deviate from Python, but it just wouldn't be a proper metaprogramming class without going over macros, templates, and Java annotations. So I hope that, even though this wasn't Python ninja-dom, it was still interesting. So I'm out of time, but if you have any questions, I'll stick around. But otherwise, I'll call lecture over. So have a good one.